I welcome you all in this lecture, which is lecture number 20 of the course Process Equipment Design, and here we are at the end of 4th week of this course. And in this lecture we will illustrate design of shell and tube heat exchanger using Bell's method with the help of one example. In this example I am going to discuss the Bell's method in detail with each and every step, right. So as far as design of shell and tube heat exchanger using Bell's method is concerned, that I have already covered in 2nd, 3rd and 4th lecture of this week, and all those steps will be applied in this example. So let us start this. So here I am having example 1, and in this example we have 20,000 kg per hour of kerosene which exits the base of kerosene site stripping column at 200 degree Celsius and to be cooled to 90 degree by exchanging heat with 62,500 kg per hour of light crude oil which is available at 50 degree Celsius. A pressure drop of 1 bar is permissible on both streams. Allowance should be made for fouling by including fouling factor of 4 into 10 power minus 4 meter square degree Celsius by watt on crude side, meter square degree Celsius per watt on crude side, and 2 into 10 power minus 4 meter square degree Celsius per watt on kerosene side. Okay. So carbon steel material is used for shell and tube, and here we have a split ring floating head shell and tube exchanger, and we have to design this exchanger using Bell's method. Okay. Now if I ask you that you are given the fouling factor of 2 fluids, right. So which fluid you should allocate to shell side and which you should allocate to tube side. Okay. The fluid having more fouling tendency should be allocated to tube side, right. So if you see, the less fouling tendency fluid is kerosene in this case because it has lesser dirt factor as compared to crude. Okay. So that is basically 2 into 10 power minus 4. So that is basically 2 into 10 power minus 4 which is less than that for crude stream, right. So kerosene should be allocated to shell side, fine. And here we have some more information like tube side, like tube dimensions are given, where in tube dimensions are given where OD of the tube, ID of the tube and total length of the tube are given along with pitch, and that is along with arrangement, and that is triangular pitch. We have to assume HI as 920 watt meter square per degree Celsius. It means tube side heat transfer coefficient is already given. So we have to focus only on shell side because Bell's method is applicable to shell side only. Number of tubes are given as 300 and baffle spacing is given as ds by 5. Now in this problem, heat transfer coefficient of tube side is already given. For example, if you are not given the tube side heat transfer coefficient, then for example, if you are not given the heat transfer coefficient of tube side and you have been asked to find out and you have been asked to design the shell and tube heat exchanger using Bell's method. So tube side calculation you should carry out as we have discussed in examples of Kern's method, okay. And then shell side calculations you have to carry out using Bell's method. So let us start the solution of this example. As you understand that Bell's method first consider heat transfer coefficient on ideal tube bank, and then different correction factors are involved in this. So the first step is to find out HOC, okay. So we have to consider calculations for HOC, and this HOC will depend on US and GS value, which is as per Kern's method. So, first of all we should find out AS value, and for that we should find out. So, first of all we should find out AS value, and for that we should calculate baffle spacing and shell dia. Okay. So, to find out shell dia we should first find out the bundle dia depending upon the arrangement and the passes. So, here I am having 1 2 pass and arrangement is triangular. So, you can consider K1 and N1 values like this. So, you can consider K1 and N1 values like this, and these values can be used to find out bundle dia, because 300 tubes are given to you. So, bundle dia you have found as 474.1 mm, and then you can find out the clearance. So, here as far as exchanger is concerned, a split ring floating head is given to you, and the bundle diameter you have already obtained as 0.47. So, that will be somewhere here. So, you can understand the value from this graph, and that value you can obtain as 58 mm, and so you can calculate shell dia. And further, if you have the shell dia, baffle spacing is given as ds by 5. So, you can consider baffle spacing like this, and then you can find out cross flow area, that is AS, which comes out as 0.01132 meter square, right. So, in this way you can calculate the cross flow area, and now you should find out velocity, Reynolds number, JH factor and heat transfer coefficient, that is HOC. So, velocity of shell side you can find considering kerosene flow rate, because that is allocated to shell side only, its density as well as AS value. Considering all these, you can find velocity in shell side at bundle equator as 0.6723. Okay. Now, if you see this problem, here we are already given the properties, okay, because the collection of property we have already discussed in Kern's method in detail, and in the similar line you can find the properties of the fluid, and as it is the repeated calculation, I am not going into detail of that, I am already providing you the properties, assuming that you can collect the property in the given method as we have discussed in Kern's method, right. So, once you have the shell side velocity, you can calculate Reynolds number, which you can find as 2.174 in 10⁻⁴. So, that is basically the turbulent region. Prandtl number you can find out, because all properties are known to you. So, this is not K, this is not R, it should be K. Okay, that should be the thermal conductivity of the fluid. So, Prandtl number you can obtain as 8.046. So, depending upon the Reynolds number like 2.17, so somewhere it will lie over here, and here you can read this value. So, value will come almost equal to 6. So, value of JH you can obtain as 5.98 into 10⁻⁻3. So, considering all these values, you can use this expression where you can neglect viscosity correction factor, and HOC you can obtain as 1780.94 watt per meter square degree Celsius. Here this W should be capital. Okay. So, in this way you can find out HOC value. Okay. Now, once you have HOC value, we should find out other correction factors, and let us see how to find out Fn, Fw, Fb and Fl. So, let us start with Fn value. Okay. So, here I am having Fn calculation, and you have already seen that we are falling, and you have already seen that fluid is falling in turbulent flow. Okay. So, we have to use the graph of Fn, for which NCV should be known to me. Okay. So, to find out NCV we should consider HB. Okay. So, first of all So, first of all I will find out HB using this expression. Okay. So, bundle diameter you have already calculated and the shell diameter. Okay. 0.5 into 0.25 because I am considering baffle spacing as 25%. Okay. So, considering all these value you can find out HB as 104.05 mm. Now, once you have HB value, you can find out NCV using this expression. So, here you already know the bundle diameter, which is this, and twice of HB I am considering, and at bottom we have PT dash, and if you see we are having triangular pitch. So, that should be arranged in this way. So, total height between two rows should be 0.87 into PT if this is the PT. Right. So, considering this we can find out NCV as 12.839 and that I have considered as 13, because whatever NCV I have obtained, that should be the complete number, right, because NCV is the number of tube rows and that can never be in decimal. Okay. So, what you have to do, you have to round it up. Okay. NCV should be round up. So, whatever value you have obtained, just consider next integer value of that, and so we can obtain NCV as 13. Okay. Now, once I am having NCV as 13, you can use this graph and somewhere here you can find the value, and if you see the value will be around 1.01. Okay. If you find the value from this graph, it should come as 1.01 FN value, right. Next I have to find out FW, that is window correction factor. Okay. Now, to find out FW you should know RW, because you are given the graph of FW and RW in books. So, RW you can consider as 2 NW by NT. NW is the number of tubes in window zone and NT is the number of tubes in bundle, and that should be equal to 2 into RA dash. Okay. So, first of all I have to find out RA dash. This is not 1, this is RA dash. Okay. And we have already discussed that RA dash will depend on bundle cut. Okay. And bundle cut, how I can define that? That should be HB by DB. Okay. So, all these parameters we have already discussed in Bell's method in lecture 2, 3 and 4 of this week. So, you can understand this. So, I am simply explaining that how to use that instead of explaining each and every parameter, right. So, if I ask you what is bundle cut, so that should be HB by DB. Okay. And HB by DB values you have already calculated, and so you can find the bundle cut as 0.22, right. Now, if you have bundle cut, you can find out RA dash from this graph. So, on x axis I am having the cut and on y axis I am having RA dash value. So, as far as cut is concerned, your cut should be somewhere here because it is 0.22, and if you are considering this, you can find out value of RA dash as 0.16 from this graph. Okay. And once you are having RA dash 0.16, RAW you can find out as 0.32, just twice of that. Okay. And once you have all these values, you can trace RW over here, that should be 0.33. So, that should be 0.33, so somewhere here it will lie, and then you can read the value from here. So, the value should come as 1.06, right. So, in this way you can find out window correction factor, and now we will focus on bypass correction factor. So, as far as bypass correction factor is concerned, here we have the expression for FB, where number of sealing strips are given as NS. Okay. So, first of all we should find out whether sealing strips are required or not, and to calculate that we should consider NS equal to 0 in this expression and to find out FB value, right. So, considering ns as equal to 0, we can find out fb based on ab and as value. Okay, ab is basically the baffle spacing into ds minus db. So, all these values are known to you. So, you can simply calculate AB. AS you have already calculated in AS you have already calculated in HOC calculations, and here I am having NS equal to 0, and for that, if so, how we can find out whether sealing strips are required or not? Okay. For that, I will put NS equal to 0 and then I will calculate FB value. If FB value is coming more than 0.6, no sealing strips are required, right. And if this is the case where no sealing strips are required, we have to find out correct FB value from this graph, where AB by AS we have already calculated, right. So, in this case FB we can find out by graph. Okay. Now, for NS equal to 0, if FB value is coming as now, for NS equal to 0, if FB value we can obtain as less than or equal to 0.6, we should use sealing strips. Okay. So, in this case, if I am putting NS equal to 0 in this expression, right. So, FB we can obtain as 0.479. Okay. So, in this case you can understand that FB is coming less than 0.6, it means we required sealing strips. Okay. So, how many sealing strips should be required? The maximum will depend on NCV value. Number of sealing strips should maximum number of sealing strips should be equal to or less than NCV by 2. Now, in this problem NCV is given as 13. So, maximum NS value we can consider as 6. Okay. So, you can consider different value of NS, and you should stop where you will find FB value more than 0.85, right. So, let us see the calculations. If I am having NS and NCV like 1 by 13, 2 by 13 in this way. So, further we can obtain AB and AS, which we have already calculated, which we have already used in FB calculation in the last equation, and here alpha value should be used as 1.35 depending upon the flow, right. So, in this case we can consider this term in the expression as lambda, and we can further reduce the FB value, and we can further reduce the FB expression like this, right, where we have the function of NS and where it is the function of NS and NCV. So, considering different NS values, because maximum NS I can use as 6, okay, and different NS value we can consider to find out FB value, and you can see we can have all FB values. Okay. So, you can consider another approach also, as we have already discussed in last lecture that sealing strips should be used in pair. So, that value should be even. Okay. So, initially I should consider NS equal to 2, then 4 and then 6 instead of 1, 2, 3, 4, 5. So, you can do that also. Now, if you consider different NS value, where you should stop, okay, as the guideline is FB value should be more than 0.85. So, you can choose 4 number as sealing strips. Okay. So, NS should be 4 in this case, because in this case FB value you can obtain as 0.896, which is more than 0.85, right. So, NS you can fix as 4. Fine. So, now we can calculate leakage correction factor. Okay. So, as far as leakage correction factor is concerned, we should use ATB, we should calculate ATB and ASB. So, ATB and ASB expressions are given over here, and here we require NW. So, NW should be NT into RA dash we have already calculated, and ATB you can find out using this expression, where CT is basically clearance between hole in baffle and tube OD. So, this CT is always equal to 8. So, this CT is always equal to 0.8 mm. Okay. So, in this way you can find out ATB value. So, considering all these value and NW you can find as 48. So, you can use this expression and you can find out ATB value as 6.03 into 10 power minus 3, right. So, here we should also consider NT minus NW. NW over here is 48, NT is 300, and next we have to find out ASB value, and to find out ASB we should also consider CS, okay, and theta B, right. So, CS, how I can obtain? CS will depend on the shell dia, and so CS will depend on the shell dia. If you see your shell dia, if you see in this problem the shell dia is 532, so it will fall in this range and in this range also. But I have told you, if I have the choice between pipe shell and plate shell, I should choose pipe shell, okay. So, this is basically the CS value. So, depending upon the shell dia we can consider CS as 1.6 as you can see here, okay. And next we have to find out theta B value, and that theta B value we can obtain from this graph, and this theta B value should be corresponding to baffle cut, right. So, here I am having 0.25 because 25% baffle cut is there. So, you can simply see the value of theta B, and that should come out as 2.1. Considering all these value you can find out ASB, okay. And this is also mentioned over here that HC by DS is 0.25, that is basically the baffle cut, and theta B should be 2.1. So, considering all these values you can find out AL, okay, and further you can find out AL by D, and further you can find out AL by AS, and the value should come as 0.69, okay. Depending upon that you can find out, so depending upon that you can find out value of beta L from this graph. So, 0.69 somewhere it will lie here, and if you see this value it should come as 0.41, right. So, considering all these values you can find FL value, and which is coming as 4965, okay. So, considering FN, FW, FB and FL values you can find out heat transfer coefficient in shell side by multiplying these with HOC value, okay. So, you can consider HS as this. So, FB value at NS equal to 4 you can find as 0.896, this we have already discussed. So, heat transfer coefficient over shell side is 848.21 watt meter square degree Celsius. So, that is basically heat transfer coefficient in shell side. Now, we should quickly cover pressure drop in shell side, okay. So, as you know that pressure drop we should consider in cross flow zone, window zone and end zone separately. So, let us start with cross flow zone. So, this is the expression for pressure drop in cross flow zone, and delta Pi is basically the pressure drop in ideal tube bank, and that you can calculate using this equation, okay. So, here US you already know NCV 13 and Reynolds number you can obtain like this, and then you can find out JH value as shown over here. So, depending upon this you can find out delta Pi value as 1026.014 Pascal, right. And after that you can find out FB dash as well as FL dash. So, FB dash, for that you should consider alpha value, otherwise all parameters will remain same. Number of sealing strip we have already fixed to 4, AB and AS value you can consider like this, and putting all these values in FB dash you can find out bypass correction factor for pressure drop as 0.722, right. And for cross flow zone And for cross flow zone we should also find out leakage correction factor. Okay. So, expression of leakage correction factor is same, only beta L dash value will differ. Fine. So, you can find out beta L dash value from this graph depending upon AL by AS, and all these value you have already calculated. So, that comes out as 0.69, and based on that beta L dash you can obtain as 0.65, and so FL value you can consider as 0.2018. So, considering delta Pi, FB dash and FL dash, you can find out pressure drop in cross flow zone as 149.49 Pascal, right. Now, we have to find out pressure drop in window zone. Okay. So, this is the expression for pressure drop in window zone. Here I have to find out NWV and UZ, and UZ is basically the geometric mean of US and UW, right. So, first of all we should find out UW, and that will depend on AW, okay, and that will depend on AW, and AW is basically the free flow area in window zone, and that we can obtain by this expression, right. So, here we have to find out RA, and so here we have to find out RA. Okay. So, once I am having bundle cut, we can find out RA dash, and once I am having waffle cut, we can find out RA using this equation, RA using this graph, right. So, I think you can read this graph, I am not going into detail of that. So, considering that RA and RA dash, you can find out NW, and you can find out NW, and that you have already calculated previously. So, that should be equal to 48, and its value should be N2 in and its value should be equal to NT into RA dash, right. So, considering this, we can find out AW, which is coming as 0.0241 meter square. Okay. Okay. So, once you have AW value, you already know the mass flow rate in shell side, that is of kerosene, and density of the kerosene. You can find out UW as 0.31568 meter per second. Okay. So, considering UW as well as US, which you have already found in HOC calculation. So, you can consider UZ as 0.4607 meter per second. Okay. And after that we should find out NWV, that is the vertical tube rows in window zone, and that should be equal to HB by PT dash. HB we have already calculated, and PT dash is 0.87 into PT, because I am considering triangular pitch. So, considering all these values, we can find out NWV as 5.0224. Okay. And here you should keep in mind that NWV should be round off, because NWV is the vertical tube rows, which will never be in a decimal, right. So, if you consider NCV, that was also the vertical tube rows, that we have made round up. Okay. So, NWV should be round off, or you can do vice versa also, like NWV should be round up or NCV should be round off, because if both values you make round off or round up, the number of tube rows will be different in bundle, right. So, here we have considered NWV as 5. So, leakage correction factor we have already calculated. So, putting all these value in delta PW, we can obtain pressure drop in window zone as 78.166 Pascal. Okay. And further we have to find out pressure drop in end zone, and the expression for that is given over here, where NWV is 5 and NCV is 13. Delta PI we have already calculated previously. So, considering all these values, you can find out delta PE as 1025.7 Pascal. Okay. So, total shell side pressure drop, that is delta PS, should be equal to 2 into delta PE, because we are having 2 end zone. Delta PC that is the pressure drop in cross flow zone into total cross flow zones, okay, and similarly pressure drop in window zone into total window zone in shell. So, here we have to find out NB value. So, NB value, that is the number of baffles, and that should be equal to capital L by LB minus 1. So, you can find out 45.98 as NB. Okay. So, because it is very close to 46, you can consider 46 also, but here I am considering 45. Here I am considering 45 as the length of the shell is fixed. Okay. So, NB should be round off, fine. So, here I am considering 45 as number of baffles. So, putting all these value in this expression, we can find out total pressure drop in shell side as 0.12146 bar, which is very less than 1 bar, which is known as the permissible limit in shell side if you read the example. So, in this way you can consider Bell's method to design the shell and tube heat exchanger, and here you can find the references to study details about this method, and here I am summarizing this video. So, in this video, design of shell and tube heat exchanger using Bell's method is illustrated with the help of one example, where tube row correction factor, window correction factor, bypass correction factor and leakage correction factors are determined, and finally heat transfer coefficient as well as pressure drop in shell side considering different correction factors are found. So, I hope you can use the Bell's method to design shell and tube heat exchanger effectively, and that is all for now. Thank you.